Okay, so we're going to look at stationary points and points of inflection. So we're looking at applications of differentiation, and these kind of points, or identifying kind of important points on a curve or on a function or for a function, is kind of a key kind of central part of the applications of differentiation. So we already know kind of that idea of kind of having turning points, and we've kind of seen when we've looked at graphs, obviously we know that graphs have particular turning points, obviously depending on the degree of the graph and what type of function it is. But with calculus, we can actually kind of calculate those actual turning points and apply that then to real world functions as well. To find maximum values, minimum values of different functions, and to be able to maximize. And that's kind of one of the real, I suppose, uses and applications of differentiation across different fields, like business, economics, kind of science, any of these kind of fields, engineering, any of these things where you might be using some sort of maths. A lot of the time it is calculus, and it is for this reason of being able to maximize and minimize. So we're going to look at the points that we need, or the points that we use, I suppose, in order to do that. So starting off with a stationary point. Now a stationary point, not stationary like pen, pencil, but stationary in the sense of kind of steady, okay, or staying the same. So if something is stationary, it's kind of not moving in a sense. So a stationary point, a point where it's not moving, and it's a point on the curve where the derivative is equal to zero. So a stationary point is a point where my derivative is equal to zero. Remember the derivative, that relationship between derivative and the tangent to the curve, the slope of tangent. The slope of the tangent. So we're really saying it's a point on the curve where the slope of the tangent is equal to zero. And we should kind of know that if the slope of the tangent is equal to zero, we're looking at a horizontal line there. We're looking at a horizontal line. So, or kind of just a straight line, I suppose. And we've three different types of these stationary points. So we can have a maximum, which obviously is here, and a maximum turning point would of course be the top, the highest point that my graph is going to reach, the highest point my function is going to reach. And we can see there the slope at that point is just a nice horizontal line. And I've written underneath this local maximum. And the reason I'm kind of specifying their local maximum is that this is the highest point for my graph within a particular range. Okay, and we're going to talk about that a little bit more in the next little section, but it's the highest point within the range maybe that we're shown. And similarly then, if we have a minimum turning point, that would be a local minimum, and it's the lowest point there. And we can see at the bottom of my graph. So looking at two parabolas there, and we can see kind of where the turning point is and how it's kind of that minimum point. And again, the slope being that horizontal, that slope of zero. The last type we have is kind of a different type, and it's kind of a specific subcategory, I suppose, if you like. It's called a saddle point. And a saddle point is, I suppose, fairly often, or comes up fairly frequently in graphs of this type. So there's a cubic graph, and where we might have three repeated roots, and it's a point where the graph kind of is increasing and it's going up, flattens out a little bit, but then continues to be increasing. So it's not considered a turning point because the graph hasn't changed direction, hasn't changed from increasing to decreasing. It was increasing, then it kind of stopped, and then it just started increasing again. So I've noted in there as well that that might be a point where the graph has three repeated roots, for example, if this was a cubic. But just knowing the difference there, that if we're asked for a stationary point, that a saddle point is still a stationary point, the slope of the tangent would still be zero. So getting more specific, I suppose we're going to look at some turning points. So a turning point is a point at which the function changes from increasing to decreasing, or vice versa. So it might go from decreasing to increasing. So a turning point can be either a maximum or a minimum, as we've said earlier there. So either a maximum turning point or a minimum turning point. And graphs can have both. They can have a highest point and a lowest point. So if we think, for example, of a cubic graph, we might have a cubic that goes like that. And we could see here we would have a maximum point up here, and we would have a minimum turning point down here. So kind of including that idea of turning point when we're talking about the maximum and the minimum just helps us to remember exactly where we're talking about. So I've noted there that at a maximum turning point, the derivative is equal to zero. So obviously that's the same for both. And also we've an added thing to remember here is to do with the second derivative. So at a maximum turning point, the second derivative is less than zero. The second derivative is negative. And at a minimum turning point, the second derivative is positive. So it's really important that you remember both of those aspects, because remembering the first will tell you it's a turning point. So we can see that it's the same step for both here, and that just tells us that it's a turning point. But in fact, it's this second derivative test It's the second derivative test here that tells us what type of turning point it is. Okay, so it's important that you have both of those aspects and that you do test out your turning points to kind of determine whether they are a maximum or a minimum turning point. So the steps I suppose we're following here to find the turning points are to find the derivative, let the derivative equal to 0, solve the equation that we get. For each value of x, find the corresponding value of y. So remembering that if we're getting a turning point, it should have an x and a y part. And then we determine the nature of the turning point, so whether it's a maximum or a minimum. So we substitute into the second derivative then to do that. So here, find the turning points of this function. So if I'm following my steps, I'm going to start by finding the first derivative. So I'm going to call it f dash x here because the function is given as f of x. That's going to give me 6x squared minus 10x minus 4. Okay, so nice quadratic function. Next, I know that at a turning point, my first derivative will be equal to 0. So remember that idea we had before, that at a turning point up here, the slope of the tangent is 0. My first derivative will be equal to 0. So just remembering that idea, really getting that ingrained here. So we're looking at a nice quadratic here. We could divide across by 2 if we want to, just to make it even nicer for us. And my two brackets here are going to be 3x plus 1 and x minus 2. That's just kind of by factorizing there. And x equals to minus a third and x equals to 2. So obviously if you wanted at that point, if you use the formula, if you're more comfortable with that, you could use your quadratic formula, but also just by factorizing there, you should be able to follow through those steps. I'm just obviously kind of skipping down to get to the main parts here. So we want to determine whether it's a maximum or a minimum, and we want to find the y values that go with each of these points here. So let's start by determining whether it's a maximum or a minimum for each point. So let's find the second derivative. That's going to be 12x minus 10. So we're going to take each of our points. I'm going to start by subbing in the minus 1/3. So 12 times minus 1/3 minus 10, and that's going to give me an overall value. Let me see, get my calculator up. So 12 by minus 1/3 minus 10 is going to give me an answer that is negative. Okay, it's going to give me a negative answer there. Okay, it's going to, oh sorry, it mistyped it. There we go. That looks more like what I was expecting. So again, still giving me a negative answer there. So what that means for us is that x equals minus 1/3 at a maximum turning point. So remember, second derivative negative means maximum turning point. Let's try the second x value here. So that's x equals to 2 minus 10. That's going to give me plus 14, which of course is greater than 0. Okay, so that therefore means that x equals 2 at a minimum turning point. So now we just need to find the y values that go with each of those, and to do that we're going back to the original functions. Okay, the original functions we had at the very start, and I'm going to be subbing into those. So 2 minus a third cubed minus 5 times minus a third squared minus 4 times minus a third minus 1. And simplifying all of that down, it's going to give me an answer of minus 8/27, which gives me a point here of minus a third minus 8/27. And I'm just going to write in max turning point for myself here, just so I know what's happening there. Okay, so that's my maximum turning point. To find my minimum turning point, same idea again. I'm going to get f of 2, just subbing in 2 there everywhere that I have x in my function. We've done a lot of this, I suppose, across these calculus chapters here, so we should be fairly comfortable with, I suppose, substituting and all of that. And obviously then this one here would be my minimum turning point. So again, just making sure we're comfortable with everything happening here. Now I said we would have a little look as well at that little note that I had, and we were saying here the maximum value on a function on a given domain may not be the local maximum. So what do we mean by that is, if I was given a function, say a cubic function of this form, and I draw my cubic here, and it goes up and it goes down, and my function continues. And say we're given this snapshot of the function here, and let's call this maybe x equals to 6, and we're asked to describe the maximum value on the domain 0 to 6. So on the x values from 0 to 6. I do have a lovely maximum turning point here, and my instinct might be say, oh yes, that's my maximum value. But in fact, we can see here that the function actually reaches a higher value at x is equal to 6. So when we're given a particular domain, it's always important to check the endpoints of the domain as well, in case your function has a higher value or a higher valued output at those endpoints than it does at the local maximum and local minimum. So I suppose that's the key thing of why we call them maybe local maximums. Just to watch out for that in some cases. So a local maximum, and kind of emphasizing that idea, it is a maximum turning point regardless of whether there's any more maximum points, but whether it is the actual maximum value of the function can depend on the function itself. So for example, the range of the function, or if we have a quadratic, then that would be the maximum value, because my quadratic will never go upwards again. Once it has reached its high point, it will just continue going downwards. So it just depends on the graph we're looking at, but it's important to just kind of have that in the back of your head, that the maximum value is not always the turning point that we have. Okay, looking at the second type of, I suppose, stationary point, or the second type of points that we have that are important here, is a point of inflection. And a point of inflection is where the curve changes from concave up to concave down, or vice versa. And what we mean by that is kind of these points where my curve maybe goes from being like this to being like this. Okay, and we're thinking, if we look at maybe a cubic, I suppose, you're thinking about a point like this one here as a point of inflection. So you're thinking about a point kind of like that one. And that's generally where your points of inflection kind of come in different curves. And again, just one to be aware of. It's where it changes from concave up to concave down. And to test or to find our points of inflection, we find the second derivative and find where that is equal to 0. Okay, so you're thinking inflection, we're thinking of inflection in people's voices. It's kind of where it kind of curves up at the end or curves down at the end. That's what we're looking for. Where is my graph kind of changing from being like this to kind of being the other way around? So it's kind of slightly different between the turning point. We can kind of see in a lot of cases there, it's kind of between your turning points. It's kind of where it's kind of going between those ones. So second example here, find the point of inflection of this graph. So we're going to find our first and then find our second derivative. So 3x squared minus 18x plus 24. Let's find the second derivative then. The second derivative is 6x minus 18. I'm going to put that second derivative equal to 0 and solve for x gives me an answer of 3. Gives me an answer of 3. I need to find the x value that goes with that, so I'm going to be subbing 3 back into my original function here. And let's just give that one a look. So 3 squared minus 9 by 3. Oh, God. Let's move that down just to make sure. By 3 squared plus 24 by 3. Gives me an answer of 18. So my point of inflection is the point 3, 18. So on that curve, that is the point where my curve would begin going from concave up to concave down. Now, another note here, a saddle point is a type of point of inflection, and it's called a horizontal point of inflection. So remembering your saddle point that we had here at the start, so the saddle point at the very top there, it's a horizontal point of inflection. It's a point where the graph changes from concave up to concave down. It's a particular type because a saddle point doesn't change kind of in terms of increasing or decreasing. It's increasing before and after the saddle point. It actually isn't changing kind of value there. So a saddle point is a stationary point of inflection. So a summary first then, maximum turning point, first derivative equals 0, second derivative less than 0, minimum turning point, first derivative equals 0, second derivative greater than 0, at a point of inflection, second derivative equal to 0, and at a saddle point, first derivative 0, second derivative also 0. And what I've said there as well, very important, remember to find the corresponding y values in every case there. And that is really, really important because the y values, I suppose, are the ones you could forget, but until you find the y value, you haven't found a point, you've just found an x value. So let's look at an exam question or two then. So we're going to start with 2014 sample paper and question 9. We're given a function, we're asked to find the value of the function for 0.2. So we're just going to be substituting in 0.2 into my function. So 0.5 by 0.2 squared plus 5 by 0.2 minus 0.98. So minus 0.5, 0.2 squared. Let's use my calculator here. And multiply, so 0.2, 0.04, 5 by 0.2 gives me 1, minus 0.98. So let's have a look. Minus 0.5 by 0.04 gives me minus 0.02 plus 1 minus 0.98. Okay, minus 0.98. And substituting all of that out there, then we're going to get 1 minus 0.02 minus 0.98, and that just gives me an answer of 0. Okay, it just gives me an answer of 0. So when I substitute that in, I just get an overall value of 0. Okay, so let's look at the next part of the question then. Show that f has a local minimum point at 511.52. Okay, 511.52. So let's differentiate our function here to look for a local minimum point. Remember, first derivative and then put it equal to 0. So that's going to be minus 1x plus 5. I'm going to put that equal to 0, which of course is going to give me that x is equal to 5. Okay, x is equal to 5. If I want to check where that value occurs, I'm going to sub it into the original function, minus 0.5 by 5 squared plus 5 by 5 minus 0.98. Okay, that's going to give me an overall answer of 11.52, which makes the point 511.52. Now what we could do in that question as well is just quickly double check the second derivative. My second derivative is my second derivative is going to be minus 1, which is going to give me, which is less than 0, which is of course a local maximum. This is a local maximum. And looking at the question there, we seem to have a quite slight mistake, perhaps I made a mistake typing it down, I'd imagine. Okay, local maximum point at 511.52. Okay, we'll not get too hung up on it, okay? Maximum point, the value still holds, I suppose. So just checking second derivative there, less than 0, so that's going to be a maximum turning point for that function there. And we can kind of see, as I was looking at the question originally, it is a negative coefficient of x squared, so it will of course have a maximum turning point as opposed to a minimum. So we just must have made a mistake typing that one down. Let's look at the next question. So the diagram below shows two functions f of x and g of x. The function f of x is given by this formula. Given that f dash 3 equals minus 12, show that k equals minus 9, where f dash k 3 is the derivative of f of x at x is equal to 3. So let's have a look. So let's get the derivative of f of x, I suppose. So the derivative of f of x is 3x squared plus 2kx plus 2kx. We want to evaluate this derivative at 3, which is of course 3 by 3 squared plus 2k by 3, and that is actually equal to minus 12. So 3 squared being 9 multiplied by 3 being 27 plus 6x equals minus 12. Or 6k, excuse me, 6k, then taking over my, oh sorry, I've forgotten the last little part of the formula there as well, excuse me, I'm going to finish it off too quickly, plus 15, okay, equals 12 as we know, plus 15 equals minus 12, okay, plus 15 equals minus 12, 6x equals minus 12, minus 15, minus 27, which means 6k equals, let's have a look, minus 12, oh sorry, it goes over here, minus 12, minus 15, minus 27, minus 54, which means that k is equal to minus 9 as expected, as kind of dictated by the question there. The function g of x then is the line that passes through the two turning points of f of x, as shown in the graph. So let's look at the graph that we have here. So we can see g of x is my line, and we can see that it indeed does pass through the two turning points of my graph there. Okay, so we're asked now to find the equation of g of x. We're asked to find the equation of g of x. Okay, so we're going to start, I suppose, by finding my turning points. Obviously, is a good place for us to start here. So finding my turning points of my function, I'm going to be differentiating here. We have differentiated already, so we know already that the derivative, we also know what k is. So let's sub that in as well. So 2 times minus 9x plus 15. So 3x squared minus 18x plus 15. And we want to know, where is this equal to 0? Let's divide across by 3 there. help simplify our question. And it's x minus 5, x minus 1 equals to 0, which means x equals 5, and which means x equals to 1. So those are my two turning points that I have for my question. Let's evaluate each of those points then to get the corresponding y values. So let's start by doing f of 5. So that's going to be 5 cubed minus 9, 5 squared, plus 15 times 5 plus 8. And let's evaluate that one here. So 5 cubed minus 9 by 5 squared plus 15 by 5 plus 8 gives me an answer of minus 17. So I get 5 minus 17. And then evaluating over here, we'll evaluate 1. So 1 cubed minus 9 by 1 plus 15 by 1 plus 8. And that's going to give me, let's just change these ones out for 1s here. And I get an answer of 15. 115. Okay, 115 here as my other turning point. So my two turning points here, so I'm presuming then that this is the point 115 and this is the point 5 minus 17. So I have 2 points on my line. If I want the equation of a line, I need two things. I need slope of the line and I need a point on the line. I have 2 points, which I can of course use to help me get the slope. So let's get the slope of g. That's going to be using my slope formula, y2 minus y1 over x2 minus x1. So 15 minus 17 over 1 minus 5. So that's 15 plus 17 over minus 4, which is going to be 32 over minus 4, which is of course minus 8. So my slope is minus 8 there. My equation of the line then, y minus y1 equals mx minus x1. So y minus, let's use the second point there, minus 8x minus 1. So y minus 15 equals minus 8x plus 8. And if we want to write it, it doesn't really matter what form we're writing the line in. We weren't given a particular form, so we just write it in this form. Minus, let me see, 23. Okay, and if we want to, we could write it in the kind of longer form there, plus 23, just to keep everything kind of positive, I suppose. Or sorry, it is positive here. So to keep just everything straight on that one there. So now we want to show that the graph of g of x contains the point of inflection of f of x. So point of inflection, we should hopefully remember, is second derivative equal to 0. So let's find the second derivative of f of x. Let's find the second derivative. So first derivative we have up here already. We found it twice actually. So first derivative was here. So second derivative would be 6x minus 18, I believe. Yeah, minus 18. We want that second derivative to be equal to 0, which means x is equal to 3. We need to find the y value that would go with that on the original function f of x. So that's going to be 3 cubed minus 9, 3 squared minus or plus 15 by 3 plus 8. Let's substitute that into our calculator then. I still have it there. So minus 9 by 3 squared plus 15 by 3 plus 8. And that gives me an answer of minus 1 for that point of inflection there. So my point of inflection is 3 minus 1. I need to show if that is on g. So to show that it's on g, I want g of 3 to be equal to minus 1. So let's give it a go. So subbing that into my function g of x over here, my equation of the line g, I'll sub it into the long version, sure. So 8 times 3 plus minus 1 minus 23 equals to 0. That gives me 24 minus 1 minus 23 equals to 0, which of course is the case. So we've confirmed that. Therefore, the point of inflection, and let's write a little explanation line. The point of inflection of f is on g. Lovely. Okay, let's look at one last question, I suppose. So an exam question here, 2023, and again, we're looking at local maximum, local minimum points. So we're given the local maximum point, or the local minimum point, excuse me, and we need to find the value of B and the value of C. So we need to have a little think about what we know about local minimum. So local minimum means dy dx equals 0. It means second derivative is positive. Okay, those are kind of the two things we have at the minute. So let's work with our first derivative. So my first derivative is 2x plus b, and we know that at my minimum point that should be equal to 0. I know that my minimum point occurs when my x value is 3, so let's sub that in. 6 plus b equals 0, which means b is equal to minus 6. Okay, we can't really do anything else by finding the second derivative. That would give us maybe a range of values, which isn't going to help us a lot. It also would result in an equation where we don't have c at all. But what we can do is use the point. We know the point is on the line, and that should mean that f of 3 should be equal to minus 1, because we haven't used the minus 1 part yet in any part of this question. So let's sub in 1. So 1 squared plus b, well, we know b now is minus 6, so minus 6 times 1 plus c, and sorry, not 1, 3. We're subbing in 3 for x, and it should all be equal to minus 1. So that's 9 minus 18 plus c equals minus 1. So I get minus 9 plus c equals minus 1, which is going to give me that c is equal to 8. So we're asked to find the value of b and c, so let's just maybe write these over here. And always, maybe no harm as well to just write out the equation as well. So x squared minus 6x plus 8. Just covering all our bases there. We can see how important it is now to have an idea of every part. Let's double check if them all done. Yeah, to have an idea of every part of that summary that we have here. So it's really important that you know all of those off and are able to use all of those fluently. There is none of those that would be given to you in the formula and tables book, for example. You could be led through it in the question, but it definitely is something that you need to be fully aware of. Know the difference between how to find a maximum and minimum turning point, what's a point of inflection, what's a saddle point, how are they related, what's a stationary point, what does it look like, the different ways that they could ask it to you, and then kind of, as we saw in the questions, they're making use of different formula and different rules that you have available to you that could end up being related.